In this video, we're going to be going over the driving forces behind contraction of the heart muscle. To recap the path of blood flow through the heart, we'll notice that it flows into the right atrium via the superior and inferior vena cava. This is low oxygen blood. And then it flows into the right ventricle or right atrium, and then into the right ventricle via the tricuspid valve, and up the pulmonary trunk through this pulmonary semilunar valve. Pulmonary trunk divides into left and right pulmonary arteries. Blood from here goes to the lungs, picks up oxygen, loses a lot of its carbon dioxide, and then comes back to the heart via these left and right pulmonary veins. Through these pulmonary veins it enters the left atrium, and then flows into the left ventricle via this bicuspid valve, from where it goes through the aorta via this aortic semilunar valve, and the aorta divides into many branches and delivers blood to the rest of the body, including the heart itself. The first branch off the aorta are the right and left coronary arteries, which deliver blood supply to the heart. But then there are other branches off the aorta which deliver blood to the rest of the body. And I went over this in a previous video, but what I forgot to mention was that blood flows from these atria to the ventricles by contraction of the atria, and blood flows from the ventricles, the right and left ventricles, into the pulmonary trunk and the aorta respectively by contraction of the right and left ventricles respectively. So blood flows from the atria into the ventricles via contraction of the atria, and from the ventricles into the pulmonary trunk, which divides into the right and left pulmonary arteries, as well as the aorta via contraction of the ventricles. In this video, we're going to be focusing on what drives that contraction. Well, the heart is comprised of muscle, myocardium, and as in the case of skeletal muscle contraction is electrically stimulated. And here's the diagram for the electrical network of the heart. And all neuronal electrical potentials, they're called action potentials. And in skeletal muscle, most membrane depolarization occurs when there's membrane depolarization of the neighboring cell. But in the heart, the sinoatrial node can actually get depolarized by itself without relying on depolarization of a neighboring cell. So this sinoatrial depolarization of the sinoatrial node is what drives contraction of the right atrium. And this signal is sent to the left atrium via Bachmann's bundle. Okay, so the right atrium contracts when this sinoatrial node is depolarized, and that signal is transmitted to the left atrium via Bachmann's bundle. So the atria contract. Shortly after the atria contract, the depolarization wave is transmitted to the atrioventricular node via these internodal tracts And the atrioventricular node, it doesn't immediately signal contraction of the ventricles. There's actually like a 1 second or 0.1 second delay between. So if you were to look at signals of a heart, or if you were to look at a diagram of heart contraction, you'll see atria contraction. Be a little delay, then there will be a signal for ventricular contraction, and that'll be a bigger signal because the ventricles are larger and more powerful than the atria. Then the next atrial contraction will occur about a second later, and then 0.1 seconds later you'll have ventricular contraction. So there is a little bit of separation between atrial contraction and ventricular contraction. And that's because this AV node actually holds the charge. It waits for the blood to collect in the right and left ventricles. And then when the blood collects in the right and left ventricles, this depolarization wave is allowed to continue through this bundle of His here, which separates into right and left bundles. The left bundle actually contains an anterior branch and a posterior branch. This should say here. So the bundle of His divides into a right bundle and a left bundle. The left bundle actually contains a left posterior branch and a left anterior branch. This posterior branch is shown as a dotted line. By convention, dotted lines tend to represent stuff that you can't see. We're looking at the heart anteriorly, so this posterior branch actually goes backward into the interior of the heart, and it's called the left posterior fascicle. I went ahead and corrected a mistake here. This is the left anterior fascicle. The right just has one branch, the right bundle. And these in turn give rise to the Purkinje fibers, and these Purkinje fibers are what actually innervate the ventricles. So after blood collects in the right ventricle, the action potential continues from the atrioventricular node through the bundle of His, then into these left and right bundles. The left bundle divides into the left posterior and anterior fascicles, while the right bundle just is one bundle. And those in turn subdivide into the Purkinje fibers, and these Purkinje fibers are what innervate the ventricles. So when the action potential reaches the Purkinje fibers, the ventricles contract. So atrial contraction is driven by this sinoatrial node, and the action potential, it depolarizes by itself, and that's different from the case of most cells, which rely on depolarization of a neighboring cell. But this sinoatrial node can actually begin the membrane depolarization process, and that depolarization wave is transmitted to the left atrium via the Bachmann's bundle. So that's how the atria contract, and that signal is transmitted to the ventricles via the atria, or it's transmitted to the atrioventricular node via these internodal tracts, and this signal is not transmitted until the blood collects in the ventricles. And during ventricular systole, so that's when the ventricles contract, this signal is transmitted through the bundle of His, which divides into left and right bundles. This is the left bundle, this is the right bundle. And remember, the left bundle in turn has a posterior fascicle and an anterior fascicle. So these bundles divide into Purkinje fibers. These Purkinje fibers are responsible for the contraction of the left and right ventricles. So when the signal reaches these Purkinje fibers, these left and right ventricles contract. The Purkinje fibers trigger contraction of the left and right ventricles. So that's basically a Cliff Notes version of the electrical system of the heart.